Good afternoon, everyone. Imagine going to your college orientation and part of the program was being asked to input a few words about what brings you to college. What do you want to pursue? What do you aspire to be? What hot topics spark your interest? And just based on these responses, you would be offered a guiding light in the form of a professor who shares similar interests with you and can act as your mentor. This is what we aim to achieve with our system, and this is our motivation. I, for one, sure know I could have made good use of such a system. To date, current recommendation systems are not able to fulfill such a task due to certain drawbacks, as requiring a user profile and large amounts of other users' data. Our approach will evade these limitations. To construct this recommender system model, we utilize data in the form of abstracts from research publications belonging to FIU faculty in the Computing and Information Sciences Department. We obtained a total of 912 records. The abstracts were chosen as the primary input as they provide an apt summary of the keywords needed to build our model.
To find the best model for our recommender system, we tried 4 algorithms. They are multinomial naive Bayes, support vector machine, decision tree, and random forests. Multinomial naive Bayes is a good dependable baseline for text classification. We chose multinomial instead of just the naive Bayes classifier because we have more than 2 labels or classes. In this case, we have 22 professors, which are the labels of our dataset. We use the function in the sciklearn library with parameters alpha equals 1 because we will be applying Laplace smoothing, fit prior false because we'll use a uniform prior, class prior none because the priors will be adjusted according to the data. We implemented k-fold validation to create balanced train test splits. At k equals 2, the accuracy was 0.57. At k equals 3, it was 0.51. K equals 4, 0.54. K equals 5, 0.54. As you may see, the best split k equals 2 gives us an accuracy of 0.57.
Coming to the support vector machine algorithm that we have implemented, support vector machines are the supervised learning models that helps to analyze the data and classify the data. We have used sklearn.svm.svc method and we tweak the parameters of regularization and the random state to get a accuracy of 0.48. We have used a linear kernel for the support vector machine and we have used a k-fold split method to randomly split the data into training and the testing samples. The other algorithm we implemented was the random forest classifier. Random forest classifier is an assemble algorithm. Assemble algorithms are those which combines the output of more than 1 or 2 algorithms based upon the majority of the decision. It's gonna classify the data. We have used sklearn.assemble.random forest classifier method to implement the algorithm. We tweak the parameters of n estimators in this particular method and we could get an accuracy of 0.35 at a k-split of 8 for this particular algorithm. And coming to the last algorithm that we have used is the decision tree classifier. Decision tree classifier classifies the data by implementing a tree. It poses a series of questions and it tries to classify the features in a form of a tree. We have used sklearn.tree.decision classifier method and we tweak the parameters of class weight and at a best split of k is equals to 5 we could get an accuracy of 0.27.
Now we will show a quick demo of our work. We read the data set into a pandas data frame and then we'll map the labels, which are the names of the professor, into numeric values. such that for each professor there is a numeric value assigned. Then we'll set the split list, which is the number of k-folds, then the classifier list with the names of the algorithms. X will be the abstract because that's where we're going to be vectorizing in order to do the classification. Y will be the label num, which is the label, the last name of the professor converted into numerical values from 0 to 21. So now we run a loop. First we start with the classifier list, and then we set the plot graph and subplots, and then we'll print the name of the classifier. Now we'll start with the k-fold split list. We'll print the number of k, and then we'll get the split for each of the train and test indexes in this split of k-fold. We'll get the x-train, x-test, y-train, and y-test datasets. We'll generate the train features by vectorizing x-train and the test features by vectorizing the x-test. Now we'll run different classifiers. If this is a multinomial naive base, we'll call the scalar method with these parameters. If this is a support vector machine, then we call this method. We're going to do a linear support vector machine. Random forest will be this, and the decision tree is this one. We're using entropy for the information gain. Now we'll fit the classifier, and then we'll use the y-train dataset in order to fit the results. We'll use cross-validation score to get the average accuracy of each k-fold, and now we'll print it. The name of the classifier, and this is the number of folds and their accuracy with the standard deviation added and a graph. We noticed the multinomial naive Bayes classifier was the one with the highest accuracy, followed by the support vector machine one. So first let's start by running our whole recommender system using the multinomial naive Bayes model. We have prepared a list of 10 test cases in order to validate the accuracy of our recommender model. Let's start with the first one. The expected output is Professor Carboner. This was correct. Second one, the expected output is Professor Chen. Correct too. If you notice, there is a link here which will take the user to the professor's webpage. So out of these 10 test cases, 2 failed. So for this small test set, the classifier has an 80% of accuracy. We also tried to do the same with the support vector machine. However, we only received an accuracy of 20% with the same test set. So we can conclude that the multinomial naive Bayes is perfect for this type of text classifications, especially when we are working only with small training sets